In this session, we explain step by step how to find out deflection, first for a cantilever beam, and second for a simply supported beam. In those two examples, we explain the first theorem of the moment area method and the second theorem of the moment area method. First, start with a cantilever beam. Load applied P at the free end span 3 meters, point A, point B. Deflected shape of this beam can be shown as this red curve, and deflection means distance between deflected curve and the original position of the beam. For example, if this beam and this is B prime, then BB prime is equal to deflection of point B. We show it by delta B. And deflection at the point like C prime is the deflection at C is equal to delta. We show it by delta C. Okay, how to find out deflection? And this is deflection. Slope. If I draw a tangent to the beam, deflected shape of the beam at A, this is the same as the original configuration of the beam, straight line AB that you can see here. That's also the same as the tangent at B at the curve beam. And there is another term here says about a new term which is called deviations. Deviation means departure from an origin or reference point with respect to a tangent. How much departure in the deflected shape of the beam from a reference point. The reference point here is the tangent line. Then we draw a tangent at A. And we wanted to find out departure of C with respect to this tangent. This CC prime is also called deviations. This is only for cantilever beam. And it's shown by T of C with respect to a tangent at A. TCA is deviations. And as I defined deflection before, CC prime, delta C, you will see that deviations and deflections are the same for cantilever beam. And the second theorem of moment area method, the moment area method, is about to calculate deviations. And if we can find deviations, we can find deflection. Second, slope of the beam at any point. How we can find the slope at any point? We must draw a tangent line at the deflection to the deflection of the deflected shape of the beam at that point. Draw a tangent line. For example, tangent line at A is the same as the initial configuration of the beam, and there is no slope between this tangent and deflected shape of the beam. The slope is 0 for A. But what about for B? If I draw the tangent at B prime to the deflected shape, this is the amount that point B of the beam is rotated, or a slope. We called it theta B. But remember, theta A is 0 because there is no angle between the original configuration of the beam and tangent at that point, at point A. The first theorem is about to calculate slope or rotation of a point after the beam is deflected. How much is that? Let's start with the first theorem. For first theorem and the second theorem, we have to draw bending moment diagram. Bending moment diagram for this beam is this diagram. 10 times 330 minus 30 kilonewton per meter. That's a point A. That's a bending moment diagram. Kilonewton meter. And that's the exercise. This is the area between A and B. Bending moment diagram area between A and B is this the area of this triangle. The first theory says that the difference between slopes of 2 points, for example, difference between the slopes of B and A, theta B minus theta A, or you can find delta theta, is equal to the area between, in the moment diagram, the area between A and B, but divided by EI. E is the modulus of elasticity, and I is the second moment area of the cross section, or moment of inertia, area moment of inertia. Then I have to show this diagram again with a difference. All values must be divided 30,000 Newton meter by A, for example, steel, 210 to the power 9 Newton per meter squared times I. Assume that there is a I-beam cross sections, 180 S, 180 times 30. 180 is the depth of the beam from top flange to the bottom flange, which is 178. This is the nominal size. Width of the flange, 98 mm. Thickness of the flange, 10 mm. And thickness of the web, 11.4 mm. I for this one is 70.65, 10 to the power minus 6 meter to power 4. Then I must write here 17.6, 10 to the power minus 6 meter to power 4. This is a very small amount. If I wanted to show it, I have to show a very small and tiny, for example, close to the origin on point M over EI here. But because this is the simplest example, other problems has maybe complicated shape of moment area. And then if you wanted to show each number in a scale, actually the shape are very close to zero. All shape for its triangle, rectangular, parabola. And in this case, we don't actually show the smallest. We just show the diagram, but with considering it that it must be divided by the value that is here is important for us. It doesn't matter that you show it in a scale or not. Okay? Then, the slope first theorem says, we can prove it in another video, that this change in the slope between 2 points is equal to the area between these two divided by area between A and I divided by that. This means that delta theta, which is equal to theta b minus theta A, which is equal to theta b minus 0 here, not always is 0, is equal to theta b, is equal to this area, half of this length, 30,000, divided by 200, 70.6 times 10 to the power 3 times 3 meters, half of it. 10 to the power 9, 10 to the power minus 6, 10 to the power 3. And these two numbers multiply each other. You will find here this angle is in radian. Okay? This is the first theorem. First theorem for the moment area method that shows you difference between tangent line. For example, if I wanted to find the difference between theta point B and C, I draw another tangent at C to the deflected shape of B, and this angle is the change, delta theta here, is theta C minus theta B is equal to the area between B and C, this area. It's changing angle. If you got theta B, you can find theta C from the first part of the solution. Okay, let's go for deflection. Deflection means deviation for cantilever beam. Second theorem of the moment area method says that deflection at deviations at any point first, because deviation and deflection are the same, you can use it interchangeably between 2 points, but for only cantilever beam. Second theorem says that deviations at any point for the beam is equal to, deviations always is a tangent deviation, is with respect to a tangent at another point. For example, deviation at B with respect to tangent at C, or deviation at B with respect to tangent at A. Okay? Then is equal to the first moment of the area between that points with respect to about a point, or with respect to a point that you are looking for its deviations. For example, I say T B with respect to A is equal. First moment, area between A and B. That's the area between A and B, the whole area. They show the whole under moment M over EI diagram. Under M over EI diagram. This area between B and A times, we draw a line vertical to the axis X, find out the centroid of the area, which is 2/3 from the vertex, 1/3 from the base. It is 3 meters, it should be 2 meters. Then is equal to 2 times the area, which is this one, half 30,000, 200, 17.6 10 to the power 3 times 3 meters. I take, this is the area. I take its moment, first moment with respect to point B. It is TBA. TBA. Then let's find out how much is TBA here. $30,000 times divided by 2 divided by 200 divided by 70.6 times 3 times 2 and divided by 1,000. It is 0.026 meter, or TBA is equal to 2.6 for 26 mm, about an inch. Okay, this is deviation of point B with respect to tangent at A. And these deviations is equal to deflection. It means that the load P 10 kilonewton applied to that I-beam and the free end moves 26 millimeter downward. The method that we use to find the deflection is called moment area method. And there are many ways. You can use integration, you can use other methods to find out deflection of a beam. This is one of the simplest calculations that we use to theorem about the deflection of a beam. First and second theorem we use here for cantilever beam to find the deflection. Then let's go for simply supported beam and find out what happened for deflection and deviation if we have simply supported beam. Then you know what is the first theorem and what is the second theorem. We use the same cross section for our beams. We show a simply supported beam. A load P is applied in the middle, 10 kilonewton. And then we wanted to find out first a slope at B, or a slope, changing a slope between A and B, first theorem. Second, how much B is moving downward, deflected of the. Let's draw the deflected shape and show the amount of deflection. This point is B, this point is B prime, and delta B is equal B. Deflection at A is 0, deflection at C is 0, but look, a slope here is not 0. Okay, if I draw a tangent at A, that's the slope at A, theta A. If I draw a tangent at C, that's the slope at C. And if I draw a tangent at B, based on the loading conditions here, this tangent is parallel to the original and there is no angle between that and the original shape configuration of the beam, then it means that the theta b here is 0. Is a base reference point to find out how much is the slope at A, how much is the slope at B. Let's draw the bending moment diagram. And we have this bending moment diagram here. If it is 1.5 m, 1.5 m, and 10 kilonewton, every support, because it is in the middle by symmetry, is 5 kilonewton times 1.57.5 kilonewton meter is amount of bending moment. This is moment diagram. Then the slope at B, you can find the slope at B. You must find slope between 2 points. Theta A and theta B is equal to area. In the bending moment diagram, divide, the first difference is only what? You must divide M by EI. Kilonewton, the unit of, this is the unit of the, unit could be different, is 1 over M. And this point between A and B, area is equal to 1/2 of 7.5 10 to power 3 Newton meter, 200 10 to power 9, 70.65 10 to power minus 6. This is meter 4. This is Oscar. It gives you in radians the amount of theta b minus theta a, but we know that theta b is 0. Then we can get slope or rotation of the beam at A. That's for the first theorem. We use the area, moment, area method, first theorem. Second theorem. Second theorem is a little different from cantilever beam. From cantilever beam, it is different because in cantilever beam, deflection and deviation was the same. But here, there is a difference between them. I show deviations here. I continue to, or draw tangent line at A completely and show deviations here. Deviation of B is departure of B from a reference point at the tangent, or tangent deviation. This is called B double prime. And this is deviation of point B. BB with respect to tangent at A. And this one, from C to C prime, is TC with respect to tangent at A. Then you will see here, deflection is 0 and deviations is the maximum with respect to A. Deviation here as B is different from deflection of B. But we can write a geometry. We must do some geometry here to find. Then BB prime is delta B. B prime, B double prime is deviations. And here, deviations, 0 with respect to itself. And deflection, also 0. I'm just looking to find delta B. Let's write some geometry. Okay, consider triangle AC supreme, which is similar to triangle, small triangle here, A, B, B, AC supreme, A, B, B double prime. This one. Write the ratio of similarity is AB over BC, small triangle, larger triangle, equals this side's BB double prime divided by CC prime. AB is the middle of the beam, B is the middle of the half of the beam, AC is the total length, is 1.5 divided by 3 equals BB, B, B double prime over CC prime. CC prime is TCA. I can find TCA by the M over EI diagram. Is the first moment of the area between C, A, and C, and then take this first moment of area with respect to point C. Instead of, I know that this centroid of the whole area is here because of symmetry. Then I found the area, I multiply it by this distance, I take the moment of the area under M over EI diagram, this is the second theorem. Then this is equal to value TCA. What about B double prime? This one is equal to delta B and BA. Okay. BB double prime from geometry is equal to deflection plus deviation TBA. What is TBA? TBA is the moment of the area between A and B with respect to B. Because we wanted to find out deviations of B with respect to A. Deviation of B. Deviation of B, you must take moment about point B. This distance, which is 1 over 5 divided by 3, half. And this is 1 meter. Then this area, half area, times 0.5 gives you TBA. And the whole area times 1.5 give you TCA. That's the second theory of moment area method. If you can find TBA and then find TCA, what we have? We have 1 over 2 TCA, you can say equals BB double prime TCA. And it is equal to BB double prime is equal to half TCA. What is BB double prime? It is delta B plus TBA equals to half TCA. Delta B equals half TCA minus TBA. That's the formula. We use some geometry, and then we reached for the deflection of point B. If you wanted to find deflection on any other point, easy. Just, for example, here, 1 meter from the A, here, for example. We call it point D. This is D prime. This is D double prime. This is TDA. Okay? TDA. And this is delta D. This value. We wanted to find delta D. Okay, write the geometry again here. Instead of AB over AC, you write AD over AC. This ratio will be changed only. The rest, instead of BB double prime, you write DD double prime. TCA is the same. Then instead of here, the delta D plus TDA is equal to D double prime. Then you continue and you reach here. The ratio here instead of 1/2 is how much? This is 1 meter divided by 3 meter is 1/3. Then delta D is 1/3 TCA minus TDA. You already calculated TCA divided by 3 minus TDA. TDA is this area. This is D. And its centroid is here, 1/3 from the base. This is 1 meter. This is 1/3 distance meter. Then this area times 1/3 is equal to TDA. Don't forget, moment diagram must be divided by EI. Don't change the shape of the moment diagram. Just for any amount of moment must be divided by EI. The important thing is this. Use the bending moment diagram. Just instead of the value, all value must be divided by value EI. That's an important point here. Do not draw another shape. Do not waste your time. Do not use a very, very small shapes that calculations make the calculations very difficult. Okay, that's the deviation, deflection for cantilever beam, for simply supported beam, and how to find them. Thank you for watching.